All right, let's dive right in. Today, we are tackling one of the most, the most fundamental building blocks in all of electronics, the BJT amplifier. We're going to break down exactly how you can analyze one, how you can design one, and really, we're going to take you from that feeling of just, I think this works, all the way to true engineering precision. And that really brings us to this quote. I absolutely love this because it just hits the nail on the head. This whole explainer, it's about crossing that exact bridge. We're going from that hobbyist hunch, the I think this will work, to the engineer's rock-solid certainty of, I know exactly what this is going to do because I can calculate. So let's get into it. What's the core problem we're even trying to solve here? Well, it all comes down to taking a signal that's, frankly, a total mess, distorted, clipped, and turning it into something clean and beautiful and, of course, amplified. But first, let's see what happens when you get it wrong. Okay, so picture this. You take an AC signal, maybe some audio from your phone, and you feed it straight into a raw transistor. What do you get? A mess. The output is just chopped up, clipped, totally distorted. So why does that happen? Well, a transistor is basically a one-way street for current. It only flows in one direction. But an AC signal, like audio, has to go both ways. It needs to push and it needs to pull. The transistor's fine with the push, but the pull? Nope. It just can't do it, so it chops that part of the signal right off. The solution, and this is the really cool part, is to completely separate our thinking into two different worlds, two universes. First up is what we'll call the DC universe. This is all about getting the transistor ready before our signal even shows up. We're setting the stage, putting everything in its place. And I think this guitar string analogy is just perfect for this. Without any prep work, a transistor is just like a loose, floppy guitar string. If you try to pluck it, you get nothing, right? It's just dead. But by applying what we call a DC bias, we're basically tightening that string. We're putting it under tension. Now, when our little AC signal comes along and plucks that string, it can actually vibrate cleanly around that new center point. And that's where we get our beautiful, clean amplification. So that tension point, that sweet spot we've created, it has a technical name. We call it the Q point, which stands for quiescent point. Basically, it's the transistor's default idling state, just sitting there waiting for a signal. And the entire job of our DC circuit, what we call the biasing circuit, is to park that Q point right in the middle of the transistor's happy place, its active region. It's now perfectly poised and ready for action. Okay, so the stage is set. Our transistor is properly biased. Now we can step into our second world, the AC universe. This is where we stop worrying about the setup and start focusing on the actual signal, that little vibration we're trying to amplify. But this brings up a huge problem. You see, transistors are non-linear. The relationship between the voltage you put in and the current you get out, it's not a nice, simple, straight line. It's a curve. And if you've done any math, you know that dealing with curves can be a real nightmare. So, how on earth do we handle that? Well, if you're dealing with really big signals that swing all over the place, then yeah, you're stuck with that messy curve. Trying to calculate gain in that situation would involve some pretty hairy calculus. It's not fun. It's really complicated. But here's the trick. It's an absolutely genius move. For the small signals we're usually trying to amplify, we don't care about the whole curve. We only care about what's happening in a tiny little area right around our Q point. And if you zoom in really, really close on any curve, what does it start to look like? A straight line. Just like that, we've linearized the problem. We turned nightmare-level math into simple high school algebra. And this whole zooming in idea leads us to the main event, the climax of this whole process, the small signal morph. We're about to literally transform our real-world circuit into a super simplified AC model. And this model, it's going to make our calculations unbelievably easy. So how do we do it? It's a three-step recipe. Step 1. From the AC signal's point of view, a big, steady DC voltage supply just looks like ground. It's a dead end. So we connect all our DC sources to ground. Step 2. Those big capacitors we used? To an AC signal, they look like wide-open highways. So we just replace them with wires, short circuits. And then step 3, the magic trick. We take the actual transistor symbol and swap it out for its new simplified AC model. So what is this mysterious new model? Well, it's actually pretty simple. It only has two parts. The first part is something called R pi,
And yeah, that's pronounced RPi. This is just the input resistance. It's what our tiny AC signal sees when it tries to go into the base of the transistor. And here's the super important part. Its value isn't some fixed number from a datasheet. No, its value is directly controlled by the DC bias current that we set up back in the DC universe.
And the second part, well, this is the real engine of the whole amplifier. It's a special component called a voltage-controlled current source. This is where all the magic happens. It's like a little machine that says, hey, for every tiny little wiggle of voltage you give me on the input, I'm going to pump out a much, much bigger proportional stream of current on the output. This is our gain engine, right?
Okay, so now we can finally bring our two universes back together. You see how it works? We use the DC universe to set the stage, to get everything just right. And those choices we made in the DC world directly control the performance we get in the AC world. This is the moment where you, as the designer, get to take complete control of your circuit. And this table here, it just sums it all up perfectly. On one hand, you have the DC job. The goal there, set the cue point, create that tension. To do that, we see the input as just a simple diode with a 0.7 volt drop. Easy. But then, for the AC job, the goal is totally different. We want to calculate the gain, that vibration. And now, that very same input doesn't look like a diode anymore. It looks like that special resistor, RPi. It's two completely different ways of looking at the exact same circuit, each for its own specific job. And after all that work, after splitting the universe in two and morphing our circuit, what's the payoff? It's this incredibly, beautifully simple formula. The voltage gain of the whole amplifier is just negative GM times RC, your collector resistor. That's it. All that complicated semiconductor physics, all those curves, it all boils down to that one elegant little equation. But here is the single most important thing I want you to take away from all of this. Look at that formula. Look closely at what's not there. Where's beta? The transistor's own internal current gain, that number that's notoriously unreliable, that changes with temperature, that's different for every single transistor you buy, it's gone. It's not in the equation. The gain of your amplifier now depends on two things: GM, a value that you control with your DC bias current, and RC, a resistor that you picked out of a part spin. You are in control now, not the unpredictable physics of the transistor. And that leaves us with a final question for you to think about. Now that you have this power, now that you can actually calculate and control the gain, the next logical step is design. So how would you do it? How would you choose your resistors to position that cue point, that sweet spot, in just the right place to get the absolute maximum possible signal swing on the output without it ever clipping or distorting? That